Hello everyone, and welcome to today's lecture on triple integration in rectangular coordinates and in non-rectangular coordinates. So today what we're going to talk about is how to compute the triple integral. So in general, the triple integral with rectangular coordinates is the easiest type of integral to evaluate. With a rectangular domain. So we've talked about how in the last class, if we have a given triple integral over some rectangular domain, we can denote this as saying the x goes from, say, we'll go 1 to 4. This is an example. The y coordinate maybe goes from 2 to 3. And say the z coordinate goes from z to 1, or from 0 to 1. So if this is the region that we're integrating over, we can always kind of draw a picture of this. Right, this region is going, say, from 1 to 4 in x, from 2 to 3, this is 1, 2, 3 in y, and from, this is just 0 to 1 in z. So it's going to look like, in general, integrating over some region omega that looks like this. A rectangular region in 3D. So the notation for this is we say that we have a triple integral of some function. Just for example, we'll take the function x squared plus y squared plus z squared. So the triple integral of this function over this region omega is the same thing as the iterated integral for x from 1 to 4, y from 2 to 3, and z from 0 to 1 of the function x squared plus y squared plus z squared. And dv is just dx dy dz, or dz dy dx. So to evaluate something like this, this is saying find the accumulation of this function over this region omega, this rectangular region omega. And just like for double integrals, this evaluation is going to be done by doing the inner integral first, and then the outer integral, and then the middle integral, and the most out integral. And you can also see this if you kind of go through and take this integral. It becomes the integral from 1 to 4 in x, from 2 to 3 in y, and the antiderivative of x squared plus y squared plus z squared with respect to z is x squared times z plus y squared times z plus z cubed over 3. This is going to be evaluated for z from 1 to 0. So when we plug in for our z integral, we end up getting that it's the integral for, again, x from 1 to 4, y from 2 to 3. Then plugging in for z will give us x squared times 1, just x squared, plus y squared times 1, plus, and then we plug in for z into z cubed over 3, it's 1/3. It's 1 cubed over 3. And to finish the calculation, you'd go through and do the double integral of this function right here. Function x squared plus y squared plus 1/3. So really the idea of triple integral or triple integration is the same idea in some sense as a double integral. We have to, essentially determine the bounds for a region and go through and evaluate each individual iterated integral to get the final value of the integral. And we're also seeing that the triple integral of this function x squared plus y squared plus z squared is the same thing as the double integral, right, of this function right here, where this is the integral from 0 to 1 of this function with respect to z. So we're also seeing that a lot of times in general when we do the triple integral, it's really the same thing as the double integral over some region R of some function. In this case it's x squared plus y squared plus z plus 1/3, which is the same thing as the antiderivative of this function right here with respect to z from 0 to 1. So a big question that you should probably be thinking of is what happens when this region is a non-rectangular domain. Because just like for double integrals, it's a little bit different. We go to integrate over a non-rectangular domain. For rectangular domains, we have Fubini's theorem. So and we'll also have Fubini's theorem, just like in 2D, we have Fubini's theorem for non-rectangular domains as well. But you have to be more careful when you're evaluating the bounds of integration. For a rectangular domain, you can evaluate this integral in any order that you want, dy, dz dx, dz dx dy, because the dv, or the volume element, can be expressed as dz dy dx, or as dy dz dx, and so on and so forth. We actually have 6 possible combinations of orders of integration that we can do for a function of 3 variables. So it turns out that Fubini's theorem, just like for a double integral, it also holds for triple integrals. We can integrate in any order that we want, but in general we have to be very, very careful about what order we choose to integrate in. Because if you choose a given order of integration, that necessarily means that you have to determine the bounds of integration for the chosen order of integration. So what I'll use for the example of this is the triple integral over non-rectangular regions. And we'll use actually as a homework example, the first web work problem of homework 5. So this asks you to not even evaluate the triple integral, but just to set up the bounds for a triple integral of some function over the region E, where E is the solid bounded by the surfaces z equals 0, z equals y, and x squared is equal to 9 minus y. Again, you might have different surfaces for your region E, but all of the web work problems are all the similar shape to this. And the idea is that we want to figure out the correct way of figuring out the bounds of integration for this example. This example is web work 5, problem 1. So this is a good example for a number of different reasons, but the main reason is that it gives us, in some sense, a picture of, in general, for a given region, how to figure out the correct bounds of integration for that region. And the key idea here is always going to be to look at the traces of the region in each individual coordinate direction. So you want to say, look at what the surface, or what the shape, the solid looks like if you look at the surface along the x-axis, along the y-axis, and along the z-axis. So in general, for a given triple integral problem, we're going to have 3 traces that we have to look at when we're determining the bounds of integration. The first trace is going to be along the z-axis. If you kind of look along the z-axis, you're going to see the xy plane. If you look along the x-axis, you're going to see the yz plane. And if you look along the y-axis, you're going to see the xz plane. And the idea is always to determine what the curves of the boundaries look like, the boundary of this shape in 3D. In this case, the boundary of E looks like along each one of these coordinate directions, what the traces in some sense look like if you look at the boundary of E along each one of these directions. So sure enough, if we look at E along the z-axis, right, the only equation that is really governing the relationship between x and y is this curve x squared minus 9 or equals 9 minus y. So this one right here. And the curve x squared equals 9 minus y is the same curve as the curve y is equal to 9 minus x squared, which is a parabola that's opening down and intersecting the x-axis at -3 and +3, and the y-axis at 9 right here. So if you were to look at this solid directly from the z-axis or along the z-axis, this is the picture that you would see. Likewise, we want to kind of look at what it looks like along the x-axis, or in the zy plane. And the relationship between z and y is given by these two equations right here. That z equals 0. That's the first big boundary equation, so z equals 0. And the second boundary equation is that z equals y, which is exactly a line in the zy plane. But we know that the maximum value of y in our domain is 9 because of these conditions right here. So we have to kind of draw a fixed line at y equals 9. And that gives us this right here as our region, or our trace of what we'll see if we look along the x-axis. So the last thing we want to look at is, what we see if we look along the y-axis, which is exactly going to be given by these two equations right here, the second and third equations. So z equals y and x squared equals 9 minus y. So if z equals y and x squared equals 9 minus y, then we also have that x squared is equal to 9 minus z. So we see the curve z is equal to 9 minus x squared when we look along the y-axis, which is exactly, again, going to be given by the same parabola right here, because we have z equals 9 minus x squared. Now you may have different coefficient numbers for your problem, so you might have a different curve than along the z-axis, but the idea is for us, we actually, in this example, have the same curve. It's just negative 3 to 3. X goes from negative 3 to 3, and y goes from 0 to 9, or z goes from 0 to 9 minus x squared. So using these three traces and the relationship between them, we can go through and actually develop a picture of what this is going to look like in 3D. In 3D, this surface is going to look like the following. We'll call this the x-axis, this the y-axis, and this the z-axis. We know that this right here, if we look directly along the z-axis, we're going to see this shape right here. So in the xy plane, we have that if this is 9, y equals 9, and this is x equals negative 3 and x equals positive 3. Oops, let me go a little bit closer there. This is the curve that we're getting. From this cross section right here. We know that at y equals 9, z is also equal to 9 because of the equation z equals y. And so we get exactly this shape right here when we look at the cross section in the zy plane. And this last curve right here is actually the intersection of the surface z equals y and x squared equals y minus 9, which looks exactly like the following curve. So it's starting here and kind of going up and down, so I make it nice. This kind of parabolic curve right here, which is exactly the shape of, looks kind of like a wedge or a doorstop. So this is all of the volume kind of contained inside here is our region E. The idea is that we only really need these three traces to determine the ultimate bounds for the final integral that we end up calculating, the triple integral. So if we call this triple integral I, the problem 1 of web work 5 asks us to go through and figure out what these bounds are going to be for a given order of integration. So for instance, if we'll say the triple integral of the function f of x, y, z in the order dz, dy, dx, we have to look at the plane, or the trace, for the outer two most variables, in this case dy, dx, and ask ourselves, how is y changing with respect to x? So in this region, x is going from -3 to 3. And as x goes from -3 to 3, y goes from a lower bound of 0 to an upper bound of this curve right here, which is 9 minus x squared. And then we have to rely on this third trace, our last trace, the last two traces you can think of in terms of finding the z-bounds, the correct z-bounds. But the main idea is that it's always based off of this surface. So in this case, we're looking at how z changes with respect to y. And we see that z starts at a lower bound of 0 and ends right here on the plane z equals y. So z goes from 0 to z equals y. And this would be the correct way of drawing out the bounds for this triple integral, in this order right here, dz, dy, dx. If we were to switch this order, I wanted to switch the order in some sense, so go, instead of dz, dy, dx, maybe do the triple integral of the function. We'll just do dy, dz, dx. Then we have to re-go up and we have to look at our traces and see how our variables are changing with respect to each other, so each other coordinate. So in this case, we have to look at the trace in the zx plane. So along the y-axis, and we see that, well, in this case, x is going from -3 to 3. And we also have that in this plane, y or z is going from 0 to the curve 9 minus x squared. So 0 to 9 minus x squared. So in this case, the x bounds and the z bounds stay similar to before, but again, you may have different numbers for your problem, so this trace might be a little bit different. And the last thing we need to ask is, as we move around in the zx plane, where is y going from, and where is what's the lower bound in y and the upper bound in y? So from the picture, as we kind of move around in this plane right here, the lower bound for y is going to be this, the plane z equals y, or like this right here, and the upper bound in y is going to be whatever the back surface is. So in this case, the surface given by x squared equals 9 minus y. So the lower bound for y is the plane z equals y, which is the same thing as y equals z, or y is equal to z for our lower bound. And our upper bound is exactly the parabola, or really it's a parabolic cylinder given by y equals 9 minus x squared. So this is going to be 9 minus x squared. And you can hopefully see that, in order to get the correct bounds of integration for a given triple integral, you have to be very careful and make sure to draw these traces and think about what the shape looks like in 3D. Because essentially each one of these bounds is a function of the other two. So the innermost bounds in this case, the z bounds in this order of integration, z depends on x. So this is a function of x right here. These two bounds are in general functions of x. And then because our innermost integral is in y, these can be functions of both z or x, which are our outer integrals, the outer variables. So this problem has you go through and get the triple integral in each separate order of integration. And the idea is that you want to kind of use this method that I've shown to get each individual order of integration, the correct bounds for that specific order of integration. So I want to consider at least one more example. This is a pretty interesting example for a number of different reasons that I'll explain kind of as we go along. But let's just consider the example of trying to find the volume formula for the region omega bounded by two cylinders of radius r. Make this capital R. Specifically, we'll take the cylinders x squared plus y squared is equal to r squared in the cylinder x squared plus z squared is equal to r squared. And I think the previous example is a good example to show how important the traces are in each individual coordinate direction. And this is going to remain true for any triple integration problem that you come across when you're trying to find the bounds. So I really want to emphasize that, and emphasize that you always want to start these problems off by drawing a picture, just like for the double integral problems that we did before. In 3D, you'll always have three separate traces. So I'll start with the xy trace here, and then move on to the other traces. So the xy trace of this region is going to consist of, first off, the circle of radius x squared plus y squared equals r squared. This is the circle that is essentially coming from the cylinder that's going along the z-axis. And it'll look like this. Where this point is negative r in x, and this point is positive r. So this is the region that we're considering in the xy plane. Now we also have the cylinder x squared plus z squared equals r squared, which if we look at it along right, the z-axis, this cylinder x squared plus z squared equals r squared, we're going to end up getting two straight vertical lines along y, because this cylinder is going along y. And these two lines correspond exactly to the trace of this equation at z equals 0, which is x squared plus y squared, or x squared plus z squared, sorry, is equal to r squared, and z equals 0 give you x squared is equal to r squared, or x is equal to plus or minus the absolute value of r, which is exactly what we have here with these two lines. So it turns out that if you go through and do this exact same thing in the zx plane, you're going to get what essentially is the same picture. Only the resulting curves are both of these curves sort of in reverse. Because this curve right here, remember, is x squared plus y squared is equal to r squared. And in the zx plane now, you have the cylinder that's going along the y-axis is x squared plus z squared equals r squared. That's giving you another circle of radius r. This is x squared plus z squared is equal to r squared. And now this equation, x squared plus y squared equals r squared, is a cylinder along the z-axis, which is again going to give you two vertical lines. Because you're looking at x squared plus y squared is equal to r squared, and this is at y equals 0. This trace at y equals 0 gives you x squared is equal to r squared, or x is equal to plus or minus the absolute value of r, which is this line right here and this line right here. So the final plane that we want to look at the trace on to get an idea of what the shape looks like is going to be the zy plane, right? It's the zy plane, and we know from before that y goes from negative r to r, and z also goes from negative r to r. And we can kind of also directly visualize both of the cylinders in the problem. Because the cylinder going along the y-axis is going to look like this. This cylinder corresponds to the cylinder z squared plus x squared is equal to r squared. This cylinder going along the y-axis. And specifically at x equals 0, this will be z is positive r and negative r. Those are the two values. And then likewise, the cylinder going along the z-axis is the cylinder x squared plus y squared is equal to r squared. That's this cylinder right here. And you can see very clearly, right, that the total region here that we got to consider is actually a rectangular region from negative r to r and negative r to r and in y and in z. That being said, the region, if you look at the upper and lower x bounds in this region, is going to be a little bit complicated. Because what we have to do is consider the intersection of these two cylinders, And the intersection of these two cylinders, right, is given by when the curve x squared plus y squared is equal to r squared, and z squared plus x squared is equal to r squared. So if I say take this equation right here and subtract this equation right here from the second equation, so subtract the first equation from the second equation, you get z squared minus y squared is equal to 0, or absolute value of z is equal to absolute value of y. And this is giving us this is definitely not super to scale, so let me move this around a little bit. It's giving us a curve of this form right here, where the origin is this intersection. Let's see if I can't change this picture a little bit to better match this. There we go. That's a little bit of a better match right there. And this is positive r and y, and this is negative r and y. So this is the trace, and what the trace kind of looks like, and what you need to consider for the trace in the zy plane, right, is all of these curves. Because if you were to say move in the order of integration the z dx dy, this would be the region that you'd have to consider, and you'd really have to be careful with the upper and lower bounds in x, because if you're say at this point in the zy plane, the upper and lower bounds in x are determined by the cylinder that's moving up and down the z-axis. So x squared plus y squared equals r squared. But if you're in this region right here, the upper and lower bounds in x are governed by the other cylinder, the cylinder going along the y-axis. And so we can very clearly see just from the traces exactly what we need to know about the bounds of integration for this region. That being said, it does help to have a nice picture of what this is looking like in three-dimensional space. So what I'm going to do is just open up my GeoGebra 3D window for a second, and we'll take a look exactly at this right here. So this is a plot of the two intersecting cylinders, okay, and we see that along the ZX axis, okay, our cross section is accurate. So along the ZX plane, or along the Y axis, you have this circle here and the two straight lines going up and down. And I even plotted out those intersections for the XY axis as well. So along this axis and this axis. And if we just rotate this so we see the trace along the ZY axis, or the ZY plane, you're seeing that exactly matches what we predicted when we went through and did the traces. So we're free to choose the order of integration that's easiest for the problem, and I'm just going to choose the standard dz dy dx because this is going to give us a relatively straightforward integral to go through and evaluate. But you can use any order of integration that you want. So the total volume of this region is going to be given by the triple integral over the region constant function 1, this is always going to be true for us. In the bounds of integration, if we integrate in the order dz, dy, dx, are going to be the following bounds. So we go to our outer two bounds here are y and x. Got to go to the xy plane. In the xy plane, x is going from negative r to r. So this determines our most outer bounds in x here, because we're going from here to here. And then as we travel from there to there, negative r to r, in y, right, we're going, say this is a given y ordinate here, or a given x ordinate right here, our y bounds are going from a lower bound of the bottom of this circle to an upper bound of the top of this circle. So they're going from here to here. This is at any point. And you want to be careful here, because you might think initially that the integral is going to be easiest to do in a circularly symmetric region or coordinate system, because the region is circularly symmetric. So you might think that polar coordinates are the easiest coordinate system to use here, and it turns out that this is actually not true. So it's a good example of how sometimes, right, the easiest coordinate system is Cartesian coordinates, even if you have an integral that's on a circular region. And we'll see that very shortly. So the bottom of this circle is given by the function y is equal to negative square root of r squared minus x squared. And the top is given by positive square root of r squared minus x squared. So therefore our bounds for y are going to be from negative square root of r squared minus x squared to positive square root of r squared minus x squared. And lastly, we think about how z changes as we move around the xy plane. So, for example, if I take this point, or this point, we ask ourselves, what's the upper and lower bounds in z at each one of these points? So we know that these are governed, right, by the cylinder that's going up and down the y-axis, or this cylinder right here. So I put the green dots right here, then I'll also shade this cylinder in green right here, because say if I were to take any one of these points, we'll just kind of move this over a little bit, and I'll move this here right here. So any one of these points in this region R, if I say take, let's say, so this point corresponds to about right here. The upper and lower bound for z are going to be determined by this surface right here. This point right here corresponds to this around here in the cross section. Just going to govern by this upper bound and this lower bound. And then this point right here corresponds to right about here on the x-axis. So it's going to be governed by this upper bound and this lower bound. And so the lower bound is given by z is equal to the negative square root of r squared minus x squared. And the upper bound here is z is equal to positive square root of r squared minus x squared. So the bounds in our integral are also these functions. You'll notice that they're the same as the bounds for y as well, but they're the same just because of the surfaces that we're dealing with here. This is the only reason. There's no connection there other than the fact that the equations governing the bounds of these intersecting surfaces are the same. But so now when we go through and evaluate this, we do the z integral first. And this is going to be this value minus this value because it's the integral of 1. So this becomes 2 times the square root of r squared minus x squared and dy dx. And at this point you might be tempted, right, looking at this integral, to say, well, these bounds are too complicated, let's go to polar coordinates. And that would not be a very good decision because this integral is actually relatively easy to evaluate in Cartesian coordinates without jumping to a new coordinate system. I will go over in the next part of this lecture how to use coordinate systems in 3D for integration. But before we do that, I want to show you that you don't always have to go to a new coordinate system. This integral is going to become 2 times the integral from negative r to r. And the thing that you notice here is that this r squared minus x squared does not depend on y at all. And our inner integral here is with respect to y. So this function is going to come out of this integral. And what is left over is the integral of the constant function 1 with respect to y, which is just y evaluated at the upper bound and the lower bound. And when we plug in here, we get 2 times the square root of r squared minus x squared. So our final answer is going to be 4 times the integral from negative r to r of the square root of r squared minus x squared multiplied by the square root of r squared minus x squared, or this squared, which is just 4 times the integral from negative r to r of r squared minus x squared, which is going to be 4 times r squared times x minus x cubed over 3 from r to negative r. And when we plug in r here, this is going to become 4 times, and ultimately what will simplify down to r squared times 2r minus 2r cubed over 3, or 8r cubed, we factor out the 2 here, and the r cubed times 1 minus 1/3, which is going to be 2/3 here times 8, so it's 16 thirds times r cubed. There you have it. That's the volume formula for the intersection of two cylinders. It's 16 thirds times r cubed, where r is the radius of each of the individual cylinders. Now, this is an important problem for a lot of different applications, because very often in mechanical engineering and many other areas, you actually have that your columns are cylinders, concrete cylinders. So this is giving you essentially the volume of the intersection of two given concrete cylinders, say. And if you're dealing with more complicated materials, an important question would be, what's the center of mass given a distributed density function for the intersection of these two regions? And we will see when we get to applications of triple integrals how to do center of mass, moment of inertia, and all the things that we talked about for double integrals for three-dimensional objects, which is the most general type of things that we typically consider in engineering applications. Another interesting problem that's related to this would be, say, to get the volume of three intersecting cylinders, right, which is a slightly more complicated integral, but can also be evaluated in this very same manner, and it's a really good practice problem. So I recommend going through and doing that, drawing the traces out and trying to find that volume.